All right, everybody, welcome back. This video lesson connects to Unit 1, Section 4 of AP Calculus, Estimating Limit Values from Tables. In this lesson, we're going to look at another way to find limits. So far we've looked at how to find them from graphs, but in this one we're going to look at how we can estimate them from a table of values. Probably the most important thing I can say today is that when we estimate the limit from a table of values, we need to realize that we can't really say with absolute certainty that it's the value of the limit. Now, when we create a table of values ourselves, we're pretty sure about that, or at least we can continue to drill down and get closer and closer to the value where we're trying to find the limit to try and get a better idea of whether our limit value is accurate, but we're never actually certain unless we, really drill down and get super duper close to that value. But most of the time, when we generate our own table, the conclusion that we're going to draw from the information that we see is going to be accurate. All right, let's look at example 1 here. Given the table below, estimate the value of limit as x approaches 3 of f of x. Now, first of all, if you've learned anything about limits so far, what you should have learned about limits so far is that this value right here, knowing the value of the function at 3, is completely unimportant in finding limit. Because the limit and the function value do not necessarily have to be the same. What is important when we're talking about finding the limit is the values that the function is approaching as x gets closer to 3. So if you look at this, the rest of these function values in the table, it looks like, from these values, it looks like the function values are getting closer and closer to -2 as x gets closer and closer to 3. So we are going to estimate that the limit as x goes to 3 of f of x here is equal to -2. Now, like I said, we're not certain. It's possible that if we put more values in this table, maybe if we put 2.99999 and 2.999999, maybe the values start shooting off towards -infinity or positive infinity. We can't really say with 100% certainty, but it is most likely in this situation that this limit is going to be -2. All right, moving on. You see here the technique excuse me, for finding the limit numerically. What we're going to do is we're going to make a table of values for the function that is close to the value where we're trying to find the limit. It says here in parentheses, I normally set my table widths to 0.001 to get close enough. Sometimes I set them smaller depending on the function, but I'm pretty consistently setting them to 0.001. Sometimes you can make them bigger. 0.01 will be good enough. But in general, from my experience, if you're using 0.0001, that's good enough. Okay? So let's go ahead and look at this first example. I think I scooched my screen there. All right, let's look at this first example. Make a table of values and estimate the following limit numerically. The limit as x, it looks like this is the limit as x approaches 4. Somehow I have a minus sign there instead of an arrow. The limit as x approaches 4 of the square root of x plus 5 minus 3 over the quantity x minus 4. So we're finding the limit as x approaches 4, and so that's the value that we want to have in the middle of our table here, 4. And like I said, I like to use 0.001 as a delta. So I'm going to count down from 4 by 1/1000ths. I'm going to fill all these values in before I even turn to my calculator, which is how I'm going to create this table of values. Now, what I could do to get this table of values is I could just one by one substitute these values into the function, but it's going to be much quicker and much easier for us to just go ahead and make a table. How you do this is fairly similar from one calculator to the next. Don't be bothered if I use a different calculator than from the one that you do. What we want to do is we want to go to our y equals screen however we get there, and we want to go ahead and make sure we type this function in correctly. So I'm going to type in the square root of x plus 5. Notice that I've put the numerator in parentheses so that my calculator handles this correctly. And for those of you who have like 84 series models with math type, it's easy for you to tell that what you're typing in is correct. My calculator is the same way. It uses what they call pretty print, and you end up with something like this that I can see I've typed this incorrectly. Now that I've got that typed in correctly, every one of the calculators should have some kind of table setup screen. I'm going to go to my table setup screen. I'm going to find table set among my function values here. And I'm going to tell my calculator, go ahead, start the table at 4. And you'll notice mine's already set for the delta table to be 0.001. And depending on what kind of calculator you have, you might see like independent, dependent down here. You want both of those to be auto if you're on an 83 or 84 series. If you're on the 89 series like me, you want your independent to be auto. And I'm going to hit enter to save that. And then I'm going to go ahead and look at my table. And you can find the table command above your top row as well. And I just scroll up from there, and now I have the value at 3.997. And if I want to see more decimal digits, or I want to see exactly what this is, because my calculator rounds it off to 5 digits, I can just scroll over there and it'll give me the values for that. And I see that this is actually approximately 0.16681. And I continue to look down at this, and then I've got 0.166676, 0.166676, and then I've got 0.166671. And then at 4, my calculator says undefined. Some calculators might say error there, depending on what kind of calculator you have. And then I go back to 4.0001, and that's 0.16662, and 0.166657, and 0.166653. Okay, now what we're looking for in this table is we're looking as these x values get closer and closer to 4, what happens with the function values? What are they getting closer and closer to? And if you can kind of imagine a number that's like in between these last two values that we have that kind of follows the same pace, it's probably going to be about 0.1666666. It looks like it's approaching 0.16 repeating to me. So I'm going to estimate that the limit of this is about 1/6, or 0.16 repeating. And that's our first example. Actually, our second example. Okay. On the next page, we're going to look at a few more problems. What I would like you to do right now is go ahead and turn to that page and pause your video and fill in those tables of values and come to your conclusion for what the limit is going to be for each of these problems, and then come back and we'll run through the answers here. I will generate them on my calculator while I'm waiting for you and just fill them in so that hopefully we can go a little bit more expediently. All right, so see you in a few moments. All right, welcome back. I'm just going to start firing in. Again, this table's centered at 2. So these are our x values. If you typed the expression incorrectly, these should be your f of x values. And usually I go to 5 or 6 digits after the decimal point when I'm putting these values in my table. You don't necessarily have to do that, but it sometimes can make it easier. If you see a few more digits, it makes it a little easier for you to see exactly what it's approaching. Although in this case, I don't think I have any difficulty deciding what this is approaching. So again, we look at what's happening as x approaches 2 from the left and as x approaches 2 from the right. And it looks like from both sides that value is getting closer and closer to -2. So that's going to be my estimate for my limit here. All right, let's look at B. B is a little different from all the other problems we're going to see here. All right, so let's go ahead and we'll fill the values into our table here. And find this limit as we approach -3. And we've got all kinds of numbers flying in here. And then we get that undefined again. And now what we have here in this example that we haven't had so far is if we look at this, we're not approaching the same numerical value from the left and the right as we look at this. As we approach from the left here, f of x is getting closer and closer to -infinity. We're getting bigger and bigger values that are negative. As we approach from the right, we're getting bigger and bigger values that are positive, so we're getting closer and closer to positive infinity as x gets closer to -3. And so in this case, we will say that our limit does not exist because it doesn't approach the same value from the left and from the right. All right. Let's fill these in here quick. And both of these are approaching 0, so I'm just going to go ahead and fill in the mindless work right off the bat for both of them. And now we fill these in, and oh boy, it takes 6 or 7 digits to see anything different in this one. In fact, if you type this up on your calculator, you probably noticed that in the rounded column, if you didn't scroll over to get more decimal digits, you probably noticed that each and every one of these f of x values, the calculator rounded to 1, which is a pretty good indicator for you that this limit is going to approach 1. And indeed, that's going to be our estimate based off of what we see here, that this limit is 1. And for the last one, we fill in the values. And again, this is one that when you looked at the values in your calculator, if you didn't scroll over to get more decimal digits, it probably was pretty clear what the limit was approaching because your calculator probably rounded it off directly to what we wanted it to be. And it looks like this limit is approaching 3. All right, that's the end of example 3. On the next page, you should see there are practice problems for you to work on. And there's also a My AP assignment down at the bottom. Make sure you complete that, those of you who are my students, before the next class. And we'll see you next time with a video related to Unit 1, Section 5, determining limits using algebraic properties of limits. All right, and I look forward to seeing you then. Have a great rest of your day.